The goal of this video is going to be to evaluate trigonometric expressions without a calculator, or for that matter the unit circle, and we're going to do this using special right triangles. The reason why we're doing this is that the unit circle is a kind of a memorization thing, and you might use it to do well on a test or a quiz, but then maybe a couple weeks later or even further on you might forget the setup of the unit circle and it's not going to go well. So we're hopefully going to improve your knowledge of why certain things are the way they are when you're evaluating trig expressions. So we're going to do that by first reviewing how to use the unit circle and maybe even why it's called the unit circle. We're then going to review special right triangles, 45-45-90s and 30-60-90s. We will then evaluate trig expressions using those two types of special right triangles, and then we want to look into the understanding of why the ratios are what they are for those 45-45-90 and 30-60-90 right triangles. So let's just say that you have this first problem right up here. It says the tangent of theta, and as I look at that reference angle, it's 60 degrees. So let's look at the fast way, and the unit circle is nice because it's pretty fast, so we're looking for the tangent of 60 degrees. And so what we're going to do, we'll just go to our handy dandy unit circle here and look at where a 60-degree angle is. And well, let's see, it gives us right here on this terminal ray, it gives us an x-coordinate of 1/2 and a y-coordinate of radical 3/2. So let's see, if this were just the sine, the answer to the sine of 60 would be this one, because I'm looking at this right here. And if this were the cosine of 60, it looks like that's the x-coordinate, so my answer for the cosine of 60 would be 1/2. But we need the tangent of 60. And we know that the tangent is equal to the sine over the cosine. So what we'll do here is take the y-coordinate and divide it by the x-coordinate and get radical 3/1, or just plain old radical 3. So that was the process of using the unit circle. Again, it seems pretty magical. You're just looking at this. Maybe you memorized the coordinates here and you knew that the x-coordinate was the cosine and the y-coordinate was the sine. Again, you maybe don't know why. So we need to talk about that. So what we're going to do now, why is it called the unit circle? Because the radius of this circle is 1. So if the radius of this circle is 1, it creates a triangle, a right triangle, where the x-coordinate would be, well, here it is, 1/2, and the y-coordinate would be radical 3/2. Again, we'll look more into that in a little bit here. But to get out at a 60-degree angle with a radius of 1, you would have to move this way 1/2 a unit, and up this way radical 3/2 units. So this is why it's called the unit circle, because that radius is 1. Alright, let's review 45-45-90 right triangles and 30-60-90 right triangles. Here's the relationship between the sides on a 45-45-90. It is isosceles. So this is, for instance, 1 and 1. Okay, it's isosceles. Sometimes you'll see it as x and x, so that this is very specific. This is less specific. So for instance, if this were 5 and 5, the hypotenuse would be 5 radical 2. Okay, we'll go into the reasons why here in a little bit. And same thing on a 30-60-90. Kind of remembering the side lengths here. The short leg is opposite the smallest angle. It's always the case on a triangle. The shortest side is opposite the smallest angle. The medium-sized side is opposite the medium angle. And the largest side is opposite the largest angle. So here would be the ratio, the setup of a 30-60-90. Less specific, more general, would be whatever this is. Let's say this is 5. This would be 2 times 5, or 10 up here, and this would be 5 radical 3. So let's talk about how to solve this problem here, which we got to be radical 3 when we did this earlier. Let's talk about how to do this using special right triangles. And by the way, most of these will create 30-degree angles, 60-degree angles, or 45-degree angles in your triangle. So look at this 60-degree angle here. I can create a right triangle by dropping an altitude to the x-axis. You're always going to drop that to the x-axis. And then if I look at my reference triangle here, 1, 2, radical 3, the short leg is 1, the hypotenuse is 2, and the long leg here is radical 3. So I know now that the tangent, thinking back to SOHCAHTOA from geometry, the tangent is the ratio of the opposite side over the adjacent side. So when I think of radical 3 over 1, I get radical 3. So no memorization there, just a little better understanding. Look at this other one here. This one's the sine of 225 degrees. This is our this is the angle 225, but we're going to use, always dropping that altitude to the x-axis, we're going to use a reference angle right in here, which is 45 degrees more than 180 degrees. So I know it doesn't look clear, but that's a 45 degree angle there. And if we look at our reference triangle here and label our sides 1, 1, radical 2, 1, 1, radical 2. Okay, we just have to make a little coordinate geometry correction here. Because I've moved left in the x direction, that's going to be negative. And because I've moved down in the y direction, that's going to be negative. And as I look at this triangle now for the sine, SOHCAHTOA, sine is opposite over hypotenuse. Opposite over hypotenuse. So our answer would be negative 1 over radical 2. Good answer. If you want to rationalize that denominator, go ahead and that would be fine too. Alright, so last thing to do here is to talk about why a 45, 45, 90 triangle has the side lengths that it does. And the description there is based on a square. So if we look at a square where all the sides are the same, and I draw a diagonal from that square, thinking back to your geometric theorems here, that is going to, on a rhombus, which a square is a type of rhombus, the diagonal will bisect each angle here. So since they were 90, they are now 45, 45. And using the Pythagorean theorem, 1 squared plus 1 squared, a squared plus b squared equals the hypotenuse squared. So we get 2 equals c squared, and c is, that hypotenuse is the square root of 2. So that's where we get the relationship in a 45, 45, 90 right triangle there. Now for the 30, 60, 90, the description there comes from an equilateral triangle, which is a type of isosceles triangle actually, and again, a geometric theorem says when you bisect the vertex angle of an isosceles triangle, it not only bisects the vertex here, making this 30 and 30, but it also bisects the base, making these sides 1 and 1. And once again, we have two right triangles here. Okay, so once again, if I use the Pythagorean theorem, a squared plus b squared equals that hypotenuse. A squared plus b squared equals the hypotenuse squared. We're looking at 1 plus b squared equals 4. B squared equals, subtract 1, 3. And b is the square root of 3. So this altitude right here has a length radical 3. So again, that's where these side lengths come from.